Hello everyone, welcome to Engineering Explained channel. In this session, I am going to take one of the problem on the first law of thermodynamics. That problem uses the steady flow energy equation of the first law of thermodynamics application. And the problem is that air flows steadily at the rate of 0.4 kg per second through an air compressor entering at 6 meter per second with a pressure of 1 bar and a specific volume of 0.85 meter cube per kg and leaving at 4.5 meter per second with a pressure of 6.9 bar and a specific volume of 0.16 meter cube per kg. The internal energy of the air leaving is 88 kilojoule per kg greater than that of the air entering. Here U2 will be greater than the 88 kilojoule per kg greater than that of the U1. Cooling water in a jacket surrounding the cylinder absorbs heat from the air at the rate of 59 watt. The heat will be transferred from the system to the surrounding of rate 59 watt. Calculate the power required to drive the compressor and the inlet and outlet cross sectional areas. In this numerical, the first part we need to find out the power required. Then that for that we are going to use the steady flow energy equation. For that all the data at the inlet and at the outlet are given. By using that we can find out the power required. Then second part, to find the cross sectional areas we are going to use the continuity equation. By using that we are going to find the area at the inlet and outlet sections. First we'll take the what are the given data are there. Mass flow rate m is 0.4 kg per second. Velocity at inlet 6 meter per second. Pressure P1 1 bar, that is 1 into 10 raised to 5 Newton per meter square. Specific volume V1 0.85 meter cube per kg. Velocity at outlet P2 4.5 meter per second. Pressure P2 6.9 bar, 6.9 into 10 raised to 5 Newton per meter square. Specific volume V2 0.16 meter cube per kg. In the problem it is given U2 is 88 kilojoule per kg greater than the U1. That U2 is equal to U1 plus 88 kilojoule per kg is taken. Therefore, U2 minus U1 is equal to 88 kilojoule per kg, that is 88,000 joule per kg. And Q1 to 2 is given, that is a negative heat transfer from the system to the surroundings. It's 59 watt. Then what to find here? Power required to drive the compressor, cross sectional area at the inlet and cross sectional area at the outlet we need to find out. First we will take we have the simplified steady flow energy equation. As we know that the steady flow energy equation is the sum of internal energy, flow work, kinetic energy and potential energy plus of Q is equal to that other side at the outlet plus of W it is there. And it can be simplified for the power output, power required. That is the work required or power required for that. Here the Q we are going to take. Okay, the other side, the what are the terms are there? If you take one side only, we are going to have the equations M multiplied with the internal energy difference, flow work difference, kinetic energy difference and potential energy difference we need to take. And here one by one term we can calculate separately and substitute in this equation to find the work required. U2 minus C1 it is given in the numerical 88,000 joule per kg. P1 P2 V2 minus of P1 V1, that is equal to 6.9 into 10 raised to 5 multiplied with the 0.16 minus of 1 into 10 raised to 5 multiplied with the 0.85, that will be these two value difference, then that will be 25,400. Then P2 square minus of V1 square by 2 is 4.5 square minus 6 square by 2 is minus 7.875. The potential energy difference is not mentioned in the numerical, therefore we'll take that as a 0 only. And after calculation of this one, we can substitute in the equation, that is heat transfer is also negative minus 59, and this term minus zero point 0.4 the mass flow rate, and remaining the 88,000, and this P2 V2 minus P1 V1 is the 25,400, and this is the minus 7.875, and this term the potential energy is taken 0, and after calculation we are going to get W is equal to minus 45,415.85 watt or 45.415 kilowatt. The work input it is, that's why we are going to get the work as a negative. And further moving, calculation of inlet and outlet cross sectional areas. For that, we have to use continuity equation. The continuity equation is the mass conservation equation. The equation based on the conservation of the mass, that is can be given as in terms of the density or can be given as in terms of the specific volume. The mass flow rate can be given as rho 1 A1 V1 or A1 V1 by second later V1, that is specific volume, because the density inverse of density is the specific volume. Okay, therefore that is equal to A2 V2 by second later V2, that is the specific volume. Okay, this equation we can use, and here the A1 and A2 we can find out from these two equations. Inlet area A1 can be given as m into specific volume by velocity, that is zero point 0.4 into 0.85 by 6, that is A1 is 0.05667 meter square. Similarly, outlet area we can find out A2 is equal to mass into specific volume by its velocity, that is A2 is equal to 0.4, 0.16 by 4.5. This is the A2. The A2 can be given as 0.01422 meter square. The cross-sectional areas at the outlet and inlet we can find out by using the continuity equation. You should know it. This is about the numerical. Thanks for watching. If you like, share, subscribe and comment.